diode as a rectifier. So we are going to have one of the important application of a diode as an rectifier. So basically this rectifier circuit is one of the part of conversion taking place from AC to DC. Suppose a system is there, it is converting an AC's input. Okay, so it is going to convert AC input to a DC output. Okay, so a rectifier will be the one of the part of this complete system. So it is not only the rectifier that is going to convert an AC input to a DC output, so it is part of that system. So basically a rectifier, where this rectifier stands in this system that converts AC input to the DC output, that we will see by using a block diagram. So basically the start of the system take place with the transformer. So we will be having AC input, that will be either voltage or current. Okay, any of the input type can be there. Okay, so here if we are providing AC, suppose AC voltage we are providing to the transformer. Okay, so this transformer will be doing either up or down of that voltage. Okay, so whatever output of this transformer will be there, that will be passed through a rectifier. Okay, so whatever output of this rectifier will be there, then again we will be requiring a filter circuit, and then after passing through filter circuit, the output will be passed through another system that will be called voltage regulator. Then we will be getting the output. This output will be a DC, a pure DC voltage or a regulated DC voltage. Okay, so basically at the input here, at the AC input, we will be providing an AC input. So AC will be like a sinusoidal AC input. Okay, so after passing through the transformer, this AC will become the same AC, but with, suppose we are doing it step down, so it will be having a smaller magnitude. Okay, so but here we can just see, so whatever this is the waveform here, this is the zero level. So this is the waveform that is having zero DC voltage. Okay, and because whatever positive, for the positive half, the waveform is having some DC value. Okay, and this DC value will be a positive DC. Similarly in the negative half there will be a negative DC. So overall the DC value will be 0 in case of the output we are getting from the transformer. That output of the transformer will be nothing but the AC voltage only, either AC or voltage or current, whatever we are providing the input. Okay, so this will be the output of the transformer. So if it is down transformer is there, so it will be making a smaller magnitude. If it is up transformer, whatever input we are providing, higher voltage at the output will be getting the same AC waveform we will be getting. So this AC waveform that is having DC value, that is 0. So here DC value is 0 because positive and negative will cancel out. So DC value will be 0. So this waveform will be passed through the rectifier. So now the rectifier, what it does basically is, so if it is the input waveform to the rectifier is, it is having a variation in positive half of the output and also the negative half. But after the rectifier, the output will be saturated only to the positive half. That means initially here some DC value was there upside and the downside is having some DC value. So overall the DC value was 0. But after getting the output from the rectifier, the output will be having some positive DC value. Okay, so here we can just write like, so here the DC value of the waveform will be somewhat greater than 0. Okay, and also it will be having some AC value. So it is not like a pure DC, it is having a AC value also. So the rectifier we can just write. So what does rectifier does is, so rectifier is going to convert a bidirectional signal. So it is up and downside signal is there. So bidirectional signal, either it is voltage or current. So bidirectional signal is going to be converted to a signal that is of unidirectional. That means it is only defined for the upper half of the output. Okay, so we can just write like this rectifier will basically convert bidirectional signal bidirectional signal to unidirectional signal. Okay, so this is the part of the rectifier that is taking the input and it is giving the output that is in unidirectional. It will be only in positive half, or it will be only in negative half based on the rectifier. Okay, so it will be only in positive. Okay, so that it will be having some DC value. Okay, so now this rectifier output is passed through a filter circuit. Okay, so once we will be passing this with a filter circuit, the output that we will be getting is some output starting with 0, and then it will be having some ripple. Okay, so this will be the output after the filter. So initially this was the rectifier output. After passing through the filter, we will get this type of output, and now this type of input will be given to the voltage regulator, and then the output at the voltage regulator that we will be getting is finally the output voltage that we will be getting at the voltage regulator circuit, that will be a pure DC. Okay, so now this will be converted to a pure DC. So here this pure DC is called a regulated DC. Okay, a regulated DC or pure DC. This uh, this waveform is called unregulated DC. And this waveform of the rectifier is called pulsating DC. Pulsating DC, or we call it unidirectional waveform, and this is bidirectional okay, and this one is the AC. So this complete system that we are getting here, like an input we are providing AC input, and we are getting the DC output. So this complete system is called DC power supply. So this complete system will be considered as DC power supply. So in the DC power supply, we will be having an AC input, and it will be converting that AC to output that will be a pure DC. So this is your power supply system. Okay, so here the role of rectifier you can just uh, see. So it will be converting a bidirectional waveform to a unidirectional waveform. This is the role of a rectifier basically. Okay, so now in rectifier we will see some points that we should be considering throughout the analysis. So that is, the first one is like we will be converting the average level of the output waveform. Whatever output waveform, that is, suppose we are getting a voltage, so that voltage will be converted uh, to find out its average value. So average value of a voltage or a current, we can directly find out like uh, v we also call it average voltage as VDC value. Okay, so this VDC is having the formula. If we are going to convert, so it will be divided by 1 by 2 pi integration from 0 to 2 pi. Whatever voltage is there, that voltage is varying with respect to time. We will be differentiating this with respect to the time. Okay, or it is having a variation with respect to omega t. So it will be voltage will be in the form of frequency and time. Okay, so this will be d omega 2. So we will be differentiating this voltage with respect to uh, d omega t. Okay, so this is how we will be finding out the average value of a voltage. Similarly, we will be finding out uh, the RMS value. Okay, so the RMS value we will be finding like voltage is there. Its RMS value is given by 1 by 2 pi integration 0 to 2 pi. Whatever voltage is there, we will be squaring that voltage, and then we will be integrating it. Okay, and after taking the integration for the complete time period, which is for what it is defined, so one complete time period 0 to 2 pi, we are considering we are going to integrate it, and after integrating we will be taking the under root, so its power will be 1 by 2. So this is how the RMS value of waveform is calculated. One more parameter is there. So once we know the DC value and once we know the RMS value, we will be finding out the RMS value. Once we have found out the RMS value, we will be finding out the ripple factor. So ripple factor basically indicates, it is represented by R. It basically indicates what is the content of AC, what is the AC content available into the converted waveform. So whatever converted output we have got, in that what is the amount of AC component is there, still some AC component is there, so that will be indicated by the uh, ripple factor term. Okay, so it is given like, so there are some formulas that you should be remembering. Okay, so this is basically under root whatever RMS value is there divided by DC value whole square minus 1. So this will be giving you out the ripple factor. Some other parameters are there that basically defines the rectifying nature of the system, what type of rectifying nature is there and how it is going to affect. So basically one is form factor. Okay, so it is represented by like V RMS divided by V DC. So by comparing these two, we can see like ripple, we can just see like it is f square minus 1. Okay, one more term is crest factor, that is defined C. So the C is whatever peak value is there divided by the RMS value. Okay, so here this ripple factor or the ripple value should be 0 ideally. Ideally this ripple factor should be 0. So if ripple factor should be 0, that means form factor should be 1. So for a ideal rectifier, this form factor should be 1 and a ripple factor should be 0. And also this crest factor, that is defined by peak value divided by RMS value. So this crest factor basically define how better this conversion is basically from AC to DC conversion, or from bidirectional to unidirectional signal is there. So what is the quality, how it has been converted, so that will be defined by the peak factor basically. So betterness of any waveform is basically decided by the crest factor, and this crest factor should be as low as possible. Okay, so it basically defines the betterness of a waveform, and C should be as low as possible. So these are some some parameters that are basically used in case of uh, rectifier, and also some parameters are there like PIV, peak inverse voltage. We have already seen what is PIV, and so some these are the parameters we will be calculating in case of the rectifier circuit. Okay, so we will start with the rectifier circuit. So basically the rectifier circuit is basically divided into two different parts. One is half wave rectifier, another one is full wave rectifier. Okay, and this full wave rectifier is further divided into two different type. One is center tapped full wave rectifier, another one is bridge full wave rectifier. Okay, so we'll go with one by one. So the first one that we will be seeing is half wave rectifier. So here basically in case of half wave rectifier, so the circuit of half wave rectifier is this one. So this is, we will be having an input. This input will be an AC input. So AC input means whatever input voltage we are providing, so this that will be having a variation with respect to time. So it is V input is equals to Vm sin omega t. Okay, so this is your time varying input signal. So that is AC signal we are providing. It will be passing through a diode, and we will be taking the output from the load resistance R. Okay, so we are taking the output from the load resistance. Okay, and we are providing the AC input. So AC input is a sinusoidal input. So this is the input waveform defined for a one time period. So from 0 to t. So this t is basically 2 pi. Okay, so this time period will be 2 pi. So from 0 to 2 pi it is defined, or from 0 to t, that is a complete one cycle is there, one cycle it is defined. So for half of the cycle uh, it is having a value of positive, and for the next half cycle it is having a value negative, and that is varying sinusoidally. Okay, so we will apply this as the input, then we will see what is the effect on the output basically. So we have already seen here. First of all, we will be considering an ideal diode. Okay, so we are going to consider if the diode is ideal. Okay, so if diode is ideal, so whenever we are applying some value that is greater than 0, so this value, this range is having a value greater than 0. So if greater than 0, that means it is a positive value. So for positive value, this diode will be on. Okay, so once it is on, it will be behaving like a short circuit. Okay, so for ideal diode, V input is greater than or equal to 0. That means diode will be forward bias. Okay, and it will be behaving like a short circuit. If the input voltage that we are getting at the input terminal of the diode, if it is less than 0, its magnitude is less than 0, then it will be like the diode is reverse bias, and it will be and behaving like an open circuit. Okay, so this is the analysis. So with respect to that, we can see here, if we consider the positive half cycle, that means for positive input of Vi, this diode will be forward bias. So if it is forward bias, it will be behaving like a short circuit. So whatever input we have applied to the diode terminal, the same input will be appearing out at the output, that is at the load resistance. Okay, so whatever voltage we have applied at the input, the same voltage will be getting at the output. Okay, so from 0 to 2 t by 2 time period, we will be getting the output that will be with this will be having the similar nature, that is what we have applied at the input. Okay, similarly for the second half from T2 to T, once we have applied, so it is a negative voltage. Okay, so once it is a negative voltage, this diode will be reverse bias. So if it is reverse bias, it will be having like an open circuit. So if open circuit is there, that means there will be no current. So the current that is flowing is zero. So if current flowing is zero, that means if current flowing through this is zero, the R multiplied by current will be equals to the output. So that current is zero, so output will also be a zero. So for the next T2 by T by 2 to T time period, the output that we will be getting is a zero. Okay, so this is basically like for positive half, it will be conducting, it will be having some current, so there will be same waveform whatever input we have applied, and the next half cycle it will be having a zero waveform. Okay, so we can just summarize it like for half wave rectifier, this will be the input signal. Okay, that is having a DC value 0, but once we are passing through a half wave rectifier, we will be getting the output like for positive half cycle it will be getting the same waveform, but for negative half cycle it will be giving out 0. So it is positive and then 0. So for one time period, if we consider for one time period, we can just see from here is like the this is the varying nature of the output, but the dc value of this waveform will be like some positive value will be there, and that dc value is defined like it will be vdc is equals to 0.318 multiplied by the maximum value. So this is the dc value of the waveform that we are obtaining at the half wave rectifier. Okay, so it is very easy to depict. Like if it is on, it will be getting the same output as the input, and if it is off, the diode is off, it will be getting the output that is 0. So it is the simplified uh, half wave rectifier. So it is called half wave because we are getting at the output only the half of the input waveform. That's why it is called half wave rectifier. Okay, so similar analysis we can do for the practical diode. Suppose this diode is a practical diode. Okay, so if diode is practical diode, then a diode can be represented by its equivalent circuit. So if it is forward bias, it will be behaving like this with a resistance. But for the analysis, this resistance is forward resistance, and this voltage plus minus will be a cut-in voltage, or we can call it knee voltage or threshold voltage. Okay, so knee voltage is V gamma, or V here represented like VK, that is knee voltage. Okay, so knee voltage is also called knee voltage or threshold voltage. Okay, so in case of practical diode, this diode will be replaced by a value of voltage source that is having the new voltage value, okay, or the threshold voltage value, and here this resistance have been neglected. Okay, so now this is the input waveform, and here we are considering the practical diode. So this diode will be conducting when, so to conduct this diode at least we should be applying 0.7 volt. So that means if this is the waveform, if this is the waveform, this is going to conduct only when the applied voltage is greater than 0.7 volt. For this region only it will be on, otherwise it will be off. Okay, that means when we are applying the input voltage that is 0 to this value, that is cut-in voltage. Okay, so up to 0.7 volt, if the input has reached from 0 to 0.7 volt, then for this region the diode will be off. So if for this region diode will be off, that means from the region 0 to 0.7 value of this input, the output will be 0. So here the output will be 0. Okay, so after that, whatever waveform is there, the same waveform will be getting at the output. That whatever V maximum is there, V maximum minus 0.7 volt. So at the output we will be getting the maximum value, that is V maximum minus Vk. Whatever the cutting voltage is there, or whatever knee voltage is there, so with threshold voltage dropping, we will be getting the output with some loss of the signal. Okay, so we are getting some loss because of this knee voltage. Okay, so this is the case of a practical diode. The similar nature will be there. The only difference is here, like we are having a value less than whatever the input we are applying. So this part of the signal will be cut, okay, at the output, and that cut will be defined by the knee voltage. Okay, knee voltage value, that is 0.7 for silicon case. So if it is silicon diode is there. Okay, so this is your half wave rectifier. Okay, so the time period for which this basically diodes are on, that is called a conduction angle. So here, in case of calculation, just we should also be noticing, like what is some parameters, like what is the output waveform we are getting, and what is the frequency. So here the frequency that we will be getting, if we talk about the frequency, the output frequency that we will be getting, that is f0, will be equals to the input frequency. So we can just see from here also. So here the frequency is like, this is the one complete cycle. So this is the time period. So with respect to that, 1 by t will be the frequency. Similarly here also, the one complete time period is the same time period that is here at the input. So that means the frequency will be same in case of half wave rectifier. So whatever output we are getting, the frequency, output frequency will be same as the input frequency. Okay, and also one term is defined called conduction angle. Conduction angle is basically, we can represent by phi. So phi basically says it is the time for which the current flows through the diode. It is basically the time for which the current flows through the diode. That means for the time this diode will be turning on, that will be considered as the conduction angle. So in case of ideal, if this is the case of ideal, so in the case of ideal, the output frequency will be same as the input frequency, and the conduction angle we can just represent by Ca. So conduction angle, that is phi, here is, it is conducting only for 0 to pi. Okay, so this is 2 pi, one time period. So a sinusoidal waveform that is periodic for 2 pi. So from 0 to pi, that means half of the time period, it is the diode is turning on. Okay, so the conduction angle will be pi. Okay, similarly, in case of here, in case of practical diode, this gap is there. There is a gap. So this gap, suppose this gap is theta. Okay, so the conduction angle for the time this diode will be conducting will be, this phi will be pi minus this value of theta. So there will be a value of theta from 1 theta from here, 1 theta from here. So 2 theta will be differentiated. So pi minus 2 theta will be less from the pi. Okay, basically, so this is the conduction angle, and this theta is basically defined as the sine inverse V gamma divided by Vm. This is not for, like you should be going with. So this is just for an understanding. We are just going through like how this loss of the signal is defined. So this defined signal is with respect to the theta, and this theta is having relation with the conduction angle. So this is how it is defined basically. So I think you have got the idea like how uh, the half wave rectifier is going to work in case of practical and ideal diode. Okay, so here one more point, like the conduction of the diode is basically, in case of practical, we can just note it like, if input is less than or equals to, if it is less than or equals to V gamma, that is knee voltage, we can say knee voltage, in that case the diode will be off. Okay, if the input voltage that is greater than the V gamma, then the diode will be on. Okay, so this is how, once the diode is on, it will be represented by its equivalent circuit, and now we will be getting the output. So from there we can get the output. So that output will, that we will be getting is, output will be, once it is on, so output will be equals to V input minus the V gamma. Okay, so this will be the output. So this is all about the half wave rectifier. So now some terms that we have defined, like what is the VDC. So DC value of the output, how we will be defining in case of here. So basically the output DC value is basically 1 by 2 pi. We have seen the formula 0 to. So first of all, here the waveform that we are getting is only defined for, so in case of this parameters we are going to find out in case of ideal case. So it is defined only for 0 to pi time period. Okay, so we will see the time period is 0 to pi, it is defined. So we will be finding 0 to pi, whatever Vm sin omega t differentiated by omega t. So once we will be differentiating, we will get the value of DC voltage, that is Vm by pi. Okay, so this is the DC value of the output waveform in case of half wave rectifier. This is the half wave rectifier case. Similarly, the Vrms we can find out. So once we will be finding out the Vrms, we can get the Vrms is equals to Vm divided by 2. Okay, and the form factor that we will be getting, that is equals to Vrms divided by VDC. Once we will be putting the value, we can get 1.57. And similarly the ripple factor that we will be getting is f square minus 1. So from there we can get this as the ripple factor. And one is crest factor. So by putting the value, peak value divided by RMS value. So peak value is Vm, RMS value, that is Vm by 2. So the crest factor is 2. Okay, and one more important parameter that we should be considering is that is PIV. So this is the calculation of peak inverse voltage. So for each type of rectifier, we will be calculating the PIV. So this was the circuit basically. Here a diode was there. So peak inverse voltage we have already seen. Peak inverse voltage is the maximum input voltage to the diode in the reverse bias case. Before that, the diode will be breaking out. Okay, so before the diode is going to break or going to damage, going to reach into the breakdown region, whatever the minimum, whatever the maximum reverse bias voltage we can apply to the diode, so that the diode has just reached before the breakdown. Okay, so whatever voltage we will be calculating, that we will be calculating such that we are providing the input in reverse bias case. So here the input voltage was there, so we are providing, like the input we are providing is the maximum input Vm that is biased in reverse bias. So this was the diode. So basically this was the circuit, we are applying the input here. Okay, this was the circuit. So we are providing the input in negative direction, that means we are reverse biasing this diode. So once we will be reverse biasing, this diode will be open circuit. So open circuit, across this open circuit we will be having a voltage that will be a PIV, the peak inverse voltage. So that reverse bias voltage will be having a nature like it will be negative, and here it will be positive. We are applying a negative voltage and a positive voltage. As it is an open circuit, the current will be flowing is 0. So if 0 current is flowing, that means the voltage drop across the resistor will be 0. So if voltage drop across the resistor is 0, so PIV will be equal to Vm. So here the PIV in case of half wave rectifier will be equals to Vm. Okay, so this is how we will be calculating the PIV. Okay, and also a parameter that is most important, that is called the efficiency, percentage efficiency. What is the efficiency of this half wave rectifier? So it is coming out to be 40.6%. Just the value you can remember. How you have got this is very complex to calculate, and that is not in, you can say, part of your syllabus. Okay, so you can just remember like what is the efficiency. So efficiency of half wave rectifier is 40.6. And also one term is called transformer utilization factor. It is basically 0.286 in case of half rectifier. Transformer utilization factor is basically the value. It basically indicates like how much utilization of transformer is going to be there into a particular circuit. So how this transformer will be utilized. So that utilization factor gives, in case of half wave rectifier, it is 0.286. So efficiency is important. You can just uh, go with it. Okay. So this was half wave rectifier. Next we will see the full wave rectifier. Okay. So basically in full wave rectifier we will first start with the center tab. Center tabbed full wave rectifier. So here basically in the half wave also, so this was the circuit we have studied. So here the input that we are seeing is, it is nothing but, so this circuit is nothing but, so in the block diagram also we have seen the output of the transformer will be getting as the input to the rectifier. So this is the rectifier circuit. So the input that it is getting is from the output of the transformer. So we can see like if transformer, this is the symbol of a transformer. Okay, so this is the transformer. Then in that transformer output we are getting a rectifier circuit. So basically it is this. So this is the primary coil and this is the secondary coil. So it is having a turn, suppose n1 is to n2 ratio is there. Okay, it is having n1 and n2 ratio. So here this is the input, primary input we call it here, primary input. This is secondary output basically. So suppose this is v1 and v2. So v1 and v2 had the relation with the number of turns. Here this n1 and n2 represent the number of turns into the coil. So it is n1 divided by n2. Okay, so here this v secondary v2 is basically the vm sin omega t that we are representing here as a vi. So this is nothing but the vi. So we are not representing this transformer again and again. So that vi is nothing but the output from the transformer. Okay, so in case of full wave rectifier, it is center tabbed. So basically in center tabbed, the transformer is there. This transformer is having a V input, and the transformer is such that the we are taking the ground as the center of the secondary coil. So this is the secondary coil. We are getting the ground from the secondary coil center. So that's why it is called center tabbed. This secondary coil center is tabbed, and from this will be the part of the output. Okay, so output we will be taking from here and from the diodes. Okay, so here it is such that it is one voltage is here. So here we are applying V input. So it is having the coil number of turns ratio 1:2 is there. That means if we are applying input V1 or Vi, we are applying the input. So output we will be getting 2Vi. Okay, so here, so the V1 should be Vi, then the V2 will be equals to 2Vi. Okay, because the number of turns is 1:2. Okay, So this V1 divided by V2 is equals to 1:2. So if Vi is the input, so 2 Vi will be the output at the secondary coil. So if this 2 Vi is divided equally into, because it is center tapped, so half of the voltage is above the center and half of the voltage will be below the center. This has been assumed. Okay. And in case of this center tap, two diodes we will be using. So in half wave we were using the one diode. Here two diodes will be used, and it is connected such that uh, both the diodes have been connected, and from there we will be getting the output. So the positive terminal of the output will be connected to these diodes. Okay, this is the positive, and the negative terminal will connect to the center tap of the transformer. Okay, so now this analysis we will be doing in case of ideal and practical cases. So basically, so here we are going to have analysis such that for the first half we will analyze. So for the first half, that is for the positive half, once we are applying the positive half input plus Vi we are applying. So this positive here and negative here will be applying, and in case of the second part also, the positive and negative will be applied. So once we are applying the positive here, so this diode will be short circuit. Okay, so first diode will be short circuit. The second one is like we are applying the negative voltage, so it will be open circuit. Okay, so this is open circuit, this is short circuit. If this is open circuit, that means there is current that is flowing is zero, but because the open circuit is there, so that part of the voltage will not be contributing to the output. So the only part that will be contributing to the output is the upper part. So from the upper part we can just see, if we are applying the positive, so this same will be with respect to the output we will be getting. So whatever input we are applying, the same out we will be getting as the output. So this is positive and this is positive, so the same voltage we will be getting. So output voltage will be the same as the input. So whatever input we are applying, the same output we will be getting. So this is the case when the positive region is being applied. Similarly, in the negative region, if we have applied the negative half, if we are applying the negative, so here it will be coming out to be a negative, and here it will be coming out to be positive, and here it is negative, and here it is positive. So if it is negative, this will be reverse bias. So if it is reverse bias, means it is open circuit, and this one is forward bias, so it will be like a short circuit. So if it is open circuit, the current will be zero, so this will not be contributing to the output. So the part that will be contributing is where the current is flowing. So this is the part where current is flowing, this is positive, so current direction will be this way. So this is the current direction, that means this will be the positive terminal, this is the negative terminal. That means the output that we will be getting in the negative half is nothing but the positive voltage. Again, in the negative half also, the negative terminal is this one connected to the output, and positive terminal is connected to positive. So in the negative half also we will be getting the output as a positive output. Okay, so in negative case, the positive output for the time period t by 2 to t. Okay, so in negative region we are getting the positive. So finally we can just see the final output that we will be getting is nothing but, by combining these two, we can just see, if we combine these two for the complete input, we can get the output that will be positive for 0 to t by 2, and again positive for t by 2 to t time period. So this is your V output. Okay, so this is the output, and the input was, just we can see, the input was this was the input. So by comparing these, we can just see what is the output frequency. If we talk about the output frequency is, here the time period has reduced. So initially it was t, this much of the time period. Now for the t by 2 time period, only one period is being completed. So the output frequency will be nothing but the 2 times the input frequency here. Okay, and also this is the case of output frequency, and also we can see what is the conduction angle. Okay, so conduction angle, that is phi. So the conduction angle for the complete circuit, the conduction angle is, it is conducting for 2 pi time period. That means for complete 360-degree, it is going to conduct. The transformer is going to, this diode is going to conduct, or the current flowing through the circuit is for both the time periods, like for the positive and negative half also. But for diodes, for each diode we can call it like, for each diode is only conducting only for 0 to t/2 time period, or 0 to pi time period. Okay, so it is only connecting for pi or 180 degrees centigrade. So for 180 degree only each of the diode is connecting, but the complete circuit is connecting for 360 degree for the complete time period. Okay, so this is the case of conduction angle, you can just see. And now we will see like what will be the case of practical diode. So similarly, this was the output. So if we talk about the practical diodes, if the diode is practical, that means it will be having some voltage drop, and that voltage drop will be with respect to the knee voltage. Okay, so negative also. So output that we will be getting is nothing but like, for the knee voltage amount, so this is the time period for which the knee voltage is there. Okay, you can see. So the output that we will be getting is, for the amount the knee voltage is not raised, the output will be 0, and then it will be coming out to be here. And it is 0 for the amount for which the knee voltage is less than, applied voltage less than 0, knee voltage. Okay, so this is the output of practical case, and this is the output in case of ideal. Okay, so the output that we will be getting is V maximum in case of practical, V maximum by minus V gamma, and in case of ideal it will be V maximum. We will be getting whatever maximum input we are applying, the same maximum output we will be getting in case of ideal case. Okay, so this is the case of full wave rectifier by using center tab concept. Okay, and also we can find out what is the GC. So in case of here, the VDC is like 2 times the Vm by pi, DC value in case of half rectifier. Whatever half rectifier diode is there, VDC value here will be this, and VRMS value will be Vm by root 2. So these values we can, you can just find out by the formula that we have discussed in earlier slides of the starting of the slide. Okay, so you can just see there is a formula, you can just put the value and you can find out the VDC and VRMS value. So once we have the VDC and VRMS, we can find out the form factor, that is coming out to be 1.1, and ripple factor it is 0.48, Crest factor coming out to be root 2, and percentage efficiency. So percentage efficiency here is 81.2%. Okay, and transformer utilization factor, that is coming out to be 0.693. Okay, and also the last point that we will see is PIV. What is PIV? So basically, so to get the PIV, first of all, what we will be doing is we will be applying the reverse bias case to the diode. So there what diode was there, so we will be applying a negative voltage. So once we are applying the negative voltage, so if it is negative, this is open circuit, and this second diode will be short circuit. Okay, so just you can see, so from there, okay, so this is negative and this is positive, this is output voltage, this is center tap. So if we are applying an opposite, we need to just reverse bias one of the diode. So suppose this diode we are reverse biasing, so here we will apply negative and here positive, and here negative and here positive. So if it is negative, this will be replaced with an open circuit. So this will be replaced by the open circuit, and this is forward bias, so this will be replaced by a short circuit. Okay, so this will be replaced by an open circuit, and this will be replaced by short circuit. This is open circuit. So if it is short circuit, so because of this, because a complete circuit is completed, so there will be a current flowing. Okay, so current flowing means if it is short circuit, Vm is the maximum input we are applying, so the same maximum voltage will be obtained across this output. So V output here, because of this current flowing, will be Vm. Okay, and also here also we have applied the Vm in negative direction. Okay, and here we need to find out the PIV. Okay, so this is how the PIV concept we will be applying here. So now in case of here, just we need to find out the what is the PIV. So by using the KVL here in this case, so this PIV will be negative, positive, and this negative and positive. So Vm and V naught will be added. So PIV in case of here will be Vm plus V naught, and V naught is nothing but Vm. So PIV here will be 2Vm. Okay, so this you need to note it like in case of center tabbed, the PIV will be 2 Vm. Okay, peak inverse voltage will be 2 Vm. The next, that is the third case, that is bridge wave rectifier. Here the diodes are connected in bridge type. Okay, so basically we are going to connect the diodes in this way. So this is the secondary output of the coil, secondary coil output. So this Vi is the AC input that we are applying to the diode. So here we will see like for ideal case, if we consider basically, so for positive half, basically for positive half, so once we are applying the positive half here, so for positive half this will be reverse bias and this will be forward bias. That means for positive half the D2 will be forward bias, and if it is positive here it will be negative, so in negative D3 will be forward bias. So these two diodes will be on and D1 and D4 diodes will be off. Okay, similarly in case of negative half, okay, so we can just see in case of negative half, suppose we have applied negative here and here positive, so if it is negative this diode will be on, so D1 will be on, and if it is positive D4 will be on, and D2 this diode and this diode D3 will be off. Okay, so once it is on and off for positive and half negative half cycle, we can just compare what will be the output. So suppose for positive half, we are applying the positive, so this is off and this is off, this will be on and this is off. So overall the circuit that we will be getting is this as the overall circuit. This is short circuit and this is short circuit. So this is the circuit. So output, that is because here or at the register this is the positive terminal and this is connected to positive, so output that we will be getting is positive. So whatever input we are applying, the same input we will be obtaining at the output for 0 to t/2 time period, that is for the positive region. Okay, similarly for the negative region or for the negative half, if we are applying the negative voltage, input voltage, AC input voltage, we are getting the output such that the diodes that are on and off, so here if it is negative this diode will be on basically and this will be off. So it will be on this way, so that the negative terminal will be connected again to the negative terminal only. Okay, so the polarity of the output is similar to the previous case. So whatever voltage we are getting in case of positive voltage at the output, similarly in case of negative also, the output that we will be getting is a positive output. Okay, so by combining these two, we can just see if this is the input waveform, the output waveform that we will be getting is both positive. Okay, so that means it is called full wave rectifier. That means the full wave of the input have been obtained at the rectifier output. And here in case of DC voltage, here the DC was 0. Here DC value will be 0.636 Vm. So that value we can just find out by the DC value formula. Okay, so the DC value VDC is equals to 1 by 2 pi 0 to 2 pi Vm sin omega t d omega t. Okay, so by calculating this, we can just get the DC value. Similarly, we can get the Vrms value. Okay, so for the Vrms value also, we are having the formula, similar formula that we are having. So the only difference is we are going to square the signal. So Vm sin omega t square d omega t. Okay, so and we are going to get the under root. So from there we can get the Vrms and VDC value. So once we have got the Vrms and VDC value, we can just see different terms we can get. Okay, so this is all about your uh, rectifier circuit. So this is the case of practical diode. If the practical diode is there, the only difference is we will be getting the output, the maximum output in that case will be V maximum minus 2 times the difference of knee voltage, because two diodes are turning on at the same time, so 2 Vk difference will be there in the maximum value. Okay, so this is the practical diode case output. And okay, the PIV calculation. So PIV calculation is one of the important. So to find out the PIV, we need to reverse bias the diode. So one of the diode is reverse bias. So once we have reverse bias, this will be a short circuit, and whatever voltage across this Vm will be there, the same voltage will be coming out to be across the PIV. So PIV in case of full wave bridge rectifier is nothing but the Vm itself. Okay, so this is all about the rectifier circuit. And the one of the important advantage of the bridge, like the bridge is having the highest transfer utilization factor, and also one of the important parameter that why bridge rectifier is advantageous is because in bridge rectifier, basically that current, the net current, DC current that flows through the circuit is basically zero. Hence the loss is basically very less. So net IDC is zero for bridge rectifier. So that's why the loss is minimum in bridge rectifier. So it is preferred basically. And also to have like here the PIV is basically PIV is less. Okay, so PIV is less. So this is one of the advantage of this bridge rectifier. Okay, that means if PIV is less, that means it can be used for high voltage applications. Okay, it can be used for high power applications, and its transfer utilization factor is highest in case of bridge rectifier, and the lower is transfer utilization factor of center tap, and the lowest is transfer utilization factor of half wave. Okay, and also this bridge rectifier uh, can be used without a transformer. That means there is no need of no need of center tap. That means it can be used without a transformer. So for a bridge rectifier, there is no need of a transformer. It can be used without a transformer also. Okay, and also here, suppose for the same output power, the smaller circuit is required in case of bridge rectifier. That means it is less costly. You can just see like it is less costly, and it is having a smaller area requirement. Okay, so this is all about the rectifier circuit, and if you have any doubt you can ask, or we can stop the class.